I am a geologist and I focus on impact cratering, and it's the most important geological process that you were never told about or rarely told about. Can you just tell me by raising your hand how many of you had some lectures on impact cratering before? Okay. There were some. That's very good, but most of you haven't heard about that much, unfortunately. And this is a process that is affecting not only the planetary surfaces, but also have shaped the planetary systems and also planetary mantles. Like, it's very important. I hope I will tell you about that in details. In the very beginning, we are going to discuss, or I'm going to discuss and ask you some questions about the basics of impact cratering. Hopefully it will give you some kind of overview, and then we'll move to the topic that I was asked to cover, which is how impact cratering is influencing the life and death in our solar system, but possibly also on in other planetary systems. Yeah, so some of because the topic is so broad, the second, some of you haven't had any exposure to this topic. So for some of you, especially the geologists that actually had some experience with impact cratering, some of the things may be very basic, but please bear with me, and maybe you can use your knowledge to later help your colleagues. Yeah, and some of the issues will be, at least in the very beginning, in the entry part, will be similar to what was just discussed, because, you know, meteorites, impact craters, there's a lot of overlap, but hopefully I will show you and tell you about them from slightly different perspective. Okay, so the first thing you need to know is that, how much, maybe someone knows, how much material is accreted daily on Earth from outside Earth? Anyone knows? Anyone would like to guess? Slightly, slightly too much, but about 100 tons daily. The estimates vary quite a lot, but this is like a middle ground. So just think about it like the great blue whale a day is falling on Earth. Luckily for us, most of this material is in the form of very small pieces. Most of this material is in the form of the pieces that are about the size of a grain of, or smaller than a grain of sand, which for us only produce those nice visible effects, but they can have very important results in other locations, which we are going to cover. However, from time to time, we have larger impacts happening. If you look here, can you see that? This white thing? This is called lunar impact flash, and this is nothing else than a piece of rock, space rock, hitting the moon. From time to time, we can even observe the crater that have been formed due to this impact. So this is an example of an impact crater that was formed in 2000, we know exactly, March 17th, 2012, I think. 13, sorry. And we have been able to measure the diameter of this crater to be 18 meters. Thanks to that, we are able to kind of back calculate the exact, or model, not exact, model the size of an impactor as well as its velocity. So this is one of the sources of information that first tell us that the impact cratering was happening not only in the past, you know, the poor dinosaurs haven't known about that, so now they are not here. And second of all, we are able to figure out exactly figure out what is the rate of the current impact flux on our surroundings. In this case, we are using the entire lunar surface as this amazing kind of experiment that similar to one that was discussed in the morning, where we have this gigantic catcher of the planetary bodies that we can observe. We were catching the solar wind with those small exposure aluminum foils. This time we are using the entire planetary or satellite to figure out how many of those things are hitting us. However, those kind of things are also hitting the Earth. The youngest impact crater on Earth was formed in 2007. This is not a long time ago. It is happening all the time. We should know about that. We should care about that. We should be prepared for it. So this one is really, really small. It was about 14 meters in diameter. It hit a field in Peru, very high up. Most probably, if it wouldn't be in Peru, but let's say somewhere in Europe where it's not 5 kilometers above the ocean level, the asteroid would break up in the air. But in this case, the crater was formed. No one was seriously injured. The only person, the only creature that was affected was a cow. That was the closest, but it survived. It was apparently only in shock, so don't worry about that. But if we'll, calculate all those things like that are hitting the moon, that are all the things that we can see in the atmosphere due to the set of cameras that are settled up all over the world, we are able to calculate how many things are hitting us. As you can see, this was also already shown to some degree here, but I will discuss it in a little bit more detail. So here you can see the mass of the impactor starting from stuff that is, smaller than the size of the grain of sand, up to the sizes of asteroids that are capable of producing seriously sized impact craters. So here, all of those parts here mostly do not produce impact craters. Those here, the black one, the triangles and rectangles, or whatever is this shape, they are producing impact craters. So you can see that we have a more or less continuous spectrum of stuff hitting us. And again, the larger the body, the less often it hits us, which is obviously quite good. And right now on Earth, we have about 200 confirmed impact craters. Unfortunately for me, most of the holes in the ground, round holes in the ground, are not impact craters. In fact, there is very, very few of them. The largest of them, anyone knows what is the largest impact crater that we know of? Rutherford in South Africa. It's 300 kilometers in diameter. Luckily for us, it was formed 2 billion years ago, because if it would be formed right now, we would be in big, big trouble. Anyone remembers what is the size of the crater that is associated with the death of dinosaurs? 180. So it was roughly twice as large. This crater, because it's 2 billion years old, is extremely eroded. So there was at least 7 kilometers of erosion. So this estimate of the size is very rough. So it could have been 350 or probably not slightly less. Maybe it's slightly underestimated. And the smallest impact crater that we know of, I've already mentioned, the 13 to 15 meters in diameter Karan-Kasper in 2007. So we have entire a spectrum of impact craters. And now, another question, silly question from me. You can see the map showing the distribution of impact craters by those dots. And you can see that those dots are distributed extremely unequally. Does it mean that the impact craters are, for example, or asteroids are preferentially hitting some places and not the other ones? For example, in Africa, yes, as you said, some places are much easier to recognize an impact crater than another ones. So this is why we have quite a lot of impact craters here, and not so many here, because here we have the ugly plants covering beautiful rocks. Plus also, impact geologists are not crazy, and if they have a chance not to go to the place where every single small creatures want to crawl into your eyeball and lay its eggs there, we prefer to work in places where it's slightly safer if there is a choice. Yeah, so that's one thing. Why? Absolutely true. Another reason why there is so many impact craters in the north of Europe and so little in the south of Europe. Any ideas? The older the areas, the more impact craters we can see, because the more time the craters, the impactors had to accumulate. So this is why in the northern part of Europe, where we have the very old rocks at the surface, we have so many impact craters, and in the southern part of Europe there are so little. And there is also a third reason. We have so many impact craters in Northern America and so few in Southern America. Any ideas, except maybe for the part where there's Amazonian, which we already discussed, but still there is a gigantic difference. One of the best parameters that correlate perfectly with the number of craters per kilometer squared is the number of people that are looking for them. So because in America, Northern America, we have so many more impact scientists that are looking for those impact craters, we know more of them. This long slide and long discussion is just to tell you that our terrestrial impact crater catalog is extremely skewed. It's very, it lacks absolutely most of the information that was, or most of the structures that were formed in the Earth, and there is definitely more of them looking to be found. So you can start tomorrow. You already also saw this plot, or a version of this plot, and you can see here the frequency of impacts versus the energy released, or the asteroid diameter, which are scaling together. And you can see that the impactors that are couple of meters in diameter, that are giving you those nice bolides, can be expected up to couple of times every year. However, the Chicxulub, so the one that killed dinosaurs, should not be formed more often than once in about 100 millions of years. So that's a good news for us. And in the moment, on the next couple of slides, I will be showing you effects that each of those sizes of asteroids that hit us have on our life. So if we are this millimeter to centimeter diameter, we are just forming those nice things on the sky. This is happening all the time, and we should be, very happily thinking about those things, except if we are in space. Okay? This is a very serious problem because the even very small pieces travel at speeds, hypervelocity speeds that are about, on average, 15 to 20 kilometers per second, which means that they are much more energetic than if you would shoot into your spaceship from a sniper gun. This is a very big problem, and this is a very big problem not only to survival of us if we want to explore moon, explore space, but also a problem for a lot of space science that is being done. For example, if we'll not account for all those micrometeorites and larger meteorites, which are obviously less likely, we are not able to calculate, we are not able to, for example, measure the very far planetary systems, because that need to be measured in infrared, because this requires a lot of heating from the shielding from the heat, and if the heat shield will be damaged by this kind of stuff, we have a problem. So those kind of things need to be taken into account, and they were already causing some problems. So for example, here is a quite famous example of a micrometeorite that hit, or a crater, microcrater that was formed on the handle on the outside of the International Space Station. That very unlucky place, because this is just very close to the place where they are getting out of the International Space Station and going around outside to do whatever they do, and because of this crater, the glove of one of the astronauts became not fully sealed. Luckily, it was very close to the entrance, so he managed to get in. But this shows that this is a very big problem. The craters, even those really small craters, are very similar in kind of general shape to the larger craters, and they have especially if they are made in metal material, they have very sharp edges. So this is also a problem that we should care about. Okay, this is something that was just shown during the previous lecture. This is fall of the meteorite in '92. This was about 1 meter in diameter. There was no crater, except if you want to count that. And this is the usual results that we have. The funny thing is that we have never noticed any person killed by a fall of a meteorite of this size. Apparently, that there was some dog killed, but no people. Okay, larger one. This was already discussed in details. 20 meter in diameter asteroid. If it's stony asteroid, it will not make an impact crater. If it's an iron, this would end up making an impact, or could have made an impact crater. And here you have one of the, again, most famous examples of Tunguska, about 50 meters in diameter body that flattened forest on the diameter of about 30 kilometers. So a large area in Siberia was just flattened. Interesting thing is that never even a small piece of the extraterrestrial material was found, even though a lot of people were looking for it, which kind of suggests to us that either aliens or the cometary body, or at least a body with a lot of with a very low strength of material and quite a lot of the kinetic energy, but not much actual mass that could be detected later on after the fall. This exactly, or more or less, the exactly sized body have produced a crater that is 1.3 kilometers in diameter. This one is located in Arizona, called Barringer Crater, about 50,000 years ago. So you can see here that 2 different bodies that had most probably similar sized had dramatically different effects that we can see right now on our planet. And of course, the most famous impact crater that killed dinosaurs was about 10 kilometers in diameter. So why do bodies that have, the 10 kilometers is a, significantly sized body, but it's nothing compared to size of the Earth. Why did it had such an effect? It's all because even though it's small, as I said, they are very fast. Their speeds are really high. They have a lot of kinetic energy. When we remember that the kinetic energy is proportional to mass, but proportional squared to the velocity. And masses can vary quite a lot. Again, we start from sizes smaller than the grain of sand. We can go to asteroids kilometers in diameter. The densities matter, but mostly to those lower impact craters. If the asteroid is large enough, it becomes less important. But the thing that is really important is the velocity. So the velocities that the bodies have when they are hitting the Earth are from about 11 to up to 70 kilometers per second. The average for the asteroidal body is about 20 kilometers per second. If you have a cometary body, you can get, higher, up to this 70. So amazing amount of kinetic energy. How much and squared? How much is it exactly? Just to give you like a, understanding. So here is the distance that is covered by distance traveled in 1 second by those objects. Here's the velocity that they have in kilometers per hour, so something that we are more used to. And here, so in 1 second, the fastest person alive will cover 11 meters. The fastest car and the one that is like just driving straight on the flat surface will cover 330 meters. Very, well, quite normal plane, about 1 kilometer, but once it's already quite high up. The highest rocket ever launched, the one that went to the Pluto system, was able after it was already traveling to go 10 kilometers per second, and absolutely average normal asteroid is able to cover 20 kilometers per second. It's amazing amount of kinetic energy, and this is why it has very the impact of asteroids with this amount of kinetic energy is causing results that are very different from what we usually see in geology. This is totally different. So here is a numerical modeling of a body that is about the size that caused formation of the Chicxulub crater, the one that killed the dinosaurs. You can see here there is it's calculated up to minus 30 kilometers. This is done by hydrocodes. So the code that is calculating how the material behaves in very extreme situation of this kind of impact. You can see here that 12 seconds after an asteroid hit, we end up with a hole in the ground that is about 15 kilometers deep. And the walls are practically vertical. Our entire impactor is just gone. It not even vaporized, it became plasma. This is why, especially for those large impact craters, we don't have impactors that made the crater. Okay, there are some people that are claiming they do. Maybe they do, but it would be rather something accompanying, not the main body that hit the Earth at this point. That would be totally gone. What does it mean that we have this kind of hole in the ground? Any ideas? Can it stay like that? No, it cannot. It's way too deep to be stable, and this is why, or partially this is why, the rocks are continuing to kind of behave like a liquid, as if it was flowing. If the crater is not too large, or depending on the size of the planetary body where the asteroid hit, for example, this is a simple crater on the moon that is about 1.5 kilometers. It stays more or less like that, so it has this classical bowl shape. The material that was thrown out from the crater just lands and it's done. However, if the crater is large, really large, it continues to bounce back. And because of that, the impact craters that are really large are not so deep, because the rocks just couldn't support this weight. They are not strong enough. And because of that, the Chicxulub impact crater is not this kind of ball-shaped thing that you could imagine. It's actually the shape like sombrero. with a material that is that has this central uplift, central hill in the very middle of the crater. However, if the craters are really, really, really large, you can end up not with a single uplift, as you can see here, but rather with a set of centrally adjusted mountain ranges. This is a Orientale Basin that is located on the moon, and luckily for us, it's located like at the side that we see just part of it. It's not in the back side of the moon, but it's on the side. Just imagine what if you would see every day on the sky, you would see this gigantic kind of ball eye looking at you. So impact craters do affect our life. As I said, because of the amazing amount of energy, kinetic energy that we have, the impact crater that is 1.4 kilometers in diameter, here is a gigantic museum with a gigantic American parking lot, just for scale, was formed by a piece that was just 50 meters in diameter. Okay, so what kind of effects does it cause for the rocks that it affects? As I said, the closer we are to the impact point, the worse it is, obviously. So the parts that are the closest to the impact point are being vaporized. Then there is a layer that is melted. And then you have the shock metamorphosed section. The further away you get, the less rocks are messed up, but you can still recognize the fact that the impact crater happened. So here you can see how the rocks, how the impact metamorphism is compared to the metamorphism in normal life. You can see here the plot of pressure versus temperature, and all the normal geology, including the very deep down geology that we have on Earth, is happening within this area of about one maybe couple of gigapascals, and temperatures up to about 1,000 degrees. Because if you get above 1,000 degrees, you melt your rock, so you kind of lose the information. However, the conditions that we have during the impact cratering process are very, very different and are marked here with this red part. So the pressures, even in those really quite small impact craters, can be and are above 5 gigapascals and can get up to 100 gigapascals. And it causes a set of very characteristic and atypical effects in your rocks. So if you get your rock and you can check if inside these rocks are characteristic minerals or characteristic features that can help you to recognize this impact crater. So for example, here you have shatter cones that are presented here. Those are quite low pressure features. You can see that they are those strange looking conical features. It's very hard to describe it, but it's easy to recognize it once you have seen many of them. This one is from a quite small impact crater in Germany called Steinheim. And they are formed, as I said, about 5 GPa. If you have the higher pressures, you, for example, form specific features within crystalline lattice of quartz or zircon. They are called planar deformation features. They generally look as if your quartz crystal was just cut into very small lamellae that are totally changed, like the crystalline lattice of the mineral just collapses. We don't know exactly how they are formed. It's kind of similar to the chondrules. There's a very funny saying that the chondrules are formed by chondrule forming processes, kind of similar with planar deformation features. We know they are there. We can describe them. We can use them in many different ways. We don't know exactly how it works, except that it's due to the passage of the shock wave through the rocks. If we increase the pressure even higher, we have the diapletic glass, which is the minerals that are within your rock look exactly the same as if they were, normal average minerals, normal average sandstone, for example, except that their crystal lattice is totally messed up. So if you will look at them under the cross-polarized light, it will be totally dark. Also, if you increase the pressure even higher, you can produce some high pressure versions of your minerals. So for example, out of quartz you can form coesite or stishovite if you reach specific values of pressure. In the past, the crater rate formation was much higher than it is right now, luckily for us. So here you can see the time before present. We are here right now. Here is the cumulative number of craters in the past. This plot was made mostly based on the Apollo era rocks and excavations. So we can see here that in the past the rate was many times higher than it is right now. However, the definition, like the exact number, is really shaky, and the longer you look at that, the more shaky it is. And it's very scary because the only way we have right now for dating all planetary surfaces in our solar system is based on crater dating. Anyone knows what is the crater dating? Yes? You can try explain.
You count the number of craters on the surface, because if it's older, it would have given you more chance for more impact events.
Exactly. It's the same thing as with, the difference between the Europe, southern and northern Europe. The older the surface, the more craters it had, because it was exposed to the situation of potentially getting hit more often. So in short, you count the number of craters, you compare it to the known number of craters of a dated surface that you dated in different way, and voila, you can determine the age of the crater. Very easy. So here you have an example. The place here, you can see that it's a young flow, lava flow on the moon, and you can see that there is definitely less impact craters than on this older surface. If you calculate that again and you compare it to the known values, you can determine the ages of all planetary surfaces. This is how we do it. However, the problem is that we don't know exactly very well how this production function looks like. There are very big errors related to the fact that, for example, one of the impact craters, the one that is kind of bounding this part of the production line, is based on a hunch and nothing else. It's based on the fact that someone grabbed a rock that someone else interpreted as if it could have been formed from an impact craters hundreds of kilometers away. So just not to say that it doesn't work, it does, but the ages that are sometimes provided based on this method should be treated with a large grain of salt. Here you can see a map with all the impact craters and impact deposits that we know of, and you can see that the ages that are shown on this plot of the craters are not very kind of representative to to the history of the Earth. So here you can see the age, the now is here, and here you have the number of the impact craters. What can we see here? Nothing. Nothing. We have nothing for that is older than 2.3 billion years. While just a moment ago I showed you this plot here. So what's wrong? We don't have information about that. This is why to get information about this very early solar system bombardment, we would have to go to other planetary bodies that do not have as intensive geology, let's call it in this way. However, we have something that is called impact ejecta and deposits. And this is a situation where we do not have an impact crater, but we have some rocks that have been affected by the impact event. So here, this is one of the nice examples. Can you see those small balls here? Do you? It kind of looks similar to chondrules, but those are not chondrules. Those are impact spherules that are formed if you have the your material that was hit by an impactor that is being melted or vaporized and then condenses and forms those structures here. Based on that, you can see that there were in the past impactors, and they had to be really gigantic because this size of the impact spherule had to be produced by impacts that were of like as large as Rutherford, those 300 kilometers or larger. Gigantic impact craters, we can see that we have some data on them, but not much. And we can see that not all of those here that are those gigantic indicators of those gigantic impactors, but those really old ones are all the features like that. And what else can we see here? Every year there is a paper that is saying, yes, during the Ordovician there was an impact spike, and then there is another paper that is saying, no, there wasn't any. Sometimes they are being published in the same journal, which is very funny, I think. So the idea is that at some point during the Ordovician there was an event in the asteroid belt that disrupted the situation. So most probably two large asteroids collided with each other, which caused an increased rate of the impactors coming to Earth. We don't know exactly yet if it's true or not because of the problems with the preservation of rocks that we see on Earth, but this is something that should and is studied. Okay, so right now I will very quickly go through the informations about the how impact craters are impacting the life. Some of those things have been already discussed during the previous lecture, so I will try to move quickly through them and focus on the ones that I care most about, which is the deadly parts. So here, first of all, the formation of our own planet is due to the gigantic impact. We don't have an impact crater from this event, obviously, because it most probably remelted either large part or entire Earth and most probably entire Moon. However, we can also, there is a good reason to think that without this particular impact, we would not be here. I mean, there could have been some microorganisms on the Earth, even without the Moon, but we, kind of more complex organism, we wouldn't make it. Any ideas why? Anyone heard about that? Think about the Mars. Mars doesn't have a Moon. Mars has very high differences in the orbital inclination. We do not move too much as a planet, and thanks to that, our climate is pretty stable. On Mars, it changes a lot. So most there is a reason to think that the more stable climate is helping us to survive better. Second thing that we owe to impactors maybe is the delivery of water. As it was discussed previously, this theory was more popular in the past. Right now I think it's kind of fading. So in the past we thought that most of the water was kind of far away in the solar system, and then it was brought to our part of the solar system by impactors. However, the analysis of the isotopic fingerprinting of ices showed that most probably the water was either brought by other asteroids, so not far away from the edges of the solar system, but rather from nearby areas. However, it's still being discussed. Next thing is the organics in meteorites. I'm sure it will be discussed more. There is some of the meteorites have a lot of organics. So, for example, this is Murchison's, and I think the total carbon is 2%, at least in this part here. But all other building blocks that are required for the formation of organics are in the meteorites and were probably brought by meteorites to Earth. Some of the meteorites also include a lot of more complex organic particles, which I'm sure a lot of you know more about than I do. However, my point is that most probably a lot of those organics that could have been formed, before a particular rock arrived on Earth were most probably either damaged or seriously changed during the impact event. Even though most of the particles that arrive on Earth are very small, most of the mass is arriving as parts of larger particles, and those larger asteroids would be destroyed, kind of remelted, and the organics would be seriously damaged. Not to say that it's not impossible to deliver. Some, obviously, we have measured that in Murchison's, for example, but it's not like most of it would be damaged. However, some experiments are suggesting that the shock waves that are going through the atmosphere can produce some of the very interesting materials, organic particles that we care about. So it's a kind of, two-way system, and we don't know yet exactly if most of the organic material was damaged or produced in this way. However, we know for sure that the impact craters are very nice location for life if the life already exists. It produces a lot of habitable niches, which may or may not be important for past Earth, but it's definitely very important for Mars, especially if we are talking about kind of extending potential habitability of the red planet, because impact craters, especially those large impact craters, are associated with significantly long-lived hydrothermal systems, even in places where those kind of situation would not be possible without the impact itself. The sources of the heat are mostly freeways, so the impact melt, which is material melted directly by the decompression of the shock wave at the impact. The impact melts can be very, very thick, can have kilometers in diameter or in thickness, and they can stay warm for millions of years, especially for those really, really large impact craters. After they are formed, they kind of behave very similarly to the volcanic volcanic melts. However, they are also kind of warmer because of the geothermal gradient. Because if you remember this numerical modeling that I shown in the very beginning, within a minute or maybe 2 minutes, literally 120 seconds, you can end up with rocks that used to be at the depths of tens of kilometers being just bounced to the surface, which means that they had a certain temperature due to the geothermal gradient, and then they are like at the surface, which they are warm. That's the point. And the third one is the kind of shockwave heating, which is especially important if you have highly porous rocks. So because of that, we know that on Earth a lot of impact crater rocks are much nicer places to live than locations that have not been hit by an asteroid. So here you have an example of all the nice things that live in the rocks that are in the crater, that the name I just forgot because, of course, but it's very high in the north, the Arctic desert, and the best place to live is in the crater because the rocks are much more porous, which means that all the microbes can just find nice habitable niches inside the rocks. Second of all, there's plenty of glass, and you probably all know how tasty glass is if you are a microbe. There often are crater lakes inside there's a hole, that there will be a crater lake very often, which means more water, which means kind of more moist situation. And there is also a lot of alteration minerals that also may be a very nice place to live for microbes. So this is why we have those kind of habitable niches on Earth, but they are obviously modeling, but also measuring and dating the alteration ages or different alteration sequences is showing us the duration of the hydrothermal system for the large impact craters like the Chicxulub, or couple of hundreds kilometers, can be millions of years, which is very significant. Maybe not for Earth. Again, we have a lot of other nice places to live for microbes due to the plate tectonics, but definitely extremely important for Mars. And everyone's favorite topic, which is lithopanspermia. Anyone knows what's lithopanspermia? Potential, very potential, nothing proven, potential possibility that the organisms may be transferred naturally from one planet to another. We don't have any proof for that, so this idea is just something that is being tested in order to see if any of the steps that are necessary can be excluded to say, no, this is not possible. For now, we haven't found anything that should definitely allow us to exclude this possibility. So first, the ejection. We know that it's possible because we have pieces of meteorites from other planetary bodies. So for example, we have meteorites from Mars. We know that it's possible to move material from Mars to Earth. It would be slightly more complicated to do it the other way around, but it's not impossible. There is a very cool paper that is found pieces of Earth on the moon within the rocks that were brought to Earth by Apollo mission. So we know that, this transfer is possible. It's all because of the impacts of larger planetary bodies that need to hit the other surface at the very specific speeds and inclinations. About 30 degrees is the most probable. And then they can eject it to the outside of the gravitational sphere influence of these planetary bodies. Most of those rocks, unfortunately, end up burned up on the sun, but some of them can reach other planetary bodies, including us. So ejection, definitely possible. But second question is, can those kind of microbes survive the ejection? So very evil people are spending quite a lot of time torturing those poor microbes in very, very brutal way by sending shock waves through the rocks that are kind of grown. The microbes are growing within the rocks. The rocks are being shocked experimentally with different methods, and then they check if the microbes survive or not. And apparently, not all types of microbes, but there are types of microbes that were tested that are able to survive up to the pressures of like absolutely crazy couple of tens of GPI. Places where you form those diaplectic glass or even coesite. This is absolutely crazy, and it definitely means that the material that was here can be first ejected, and then if there are any microbes, then they can potentially survive ejection process. The second thing is that they have to, and here's the example of the infamous Martian meteorite with potential microbes that you have probably heard about in the past. So the transfer, we know, thanks to the fact that we have those meteorites from Mars, we know that it's possible to deliver them to Earth. And the transfer, but the largest problem with the transfer is that the potential microbes need to be exposed to the cosmic environment for quite a long time. So the transfer is taking a couple of tens to a couple of hundreds of thousands of years at minimum. The microbes need to be able to survive that, and obviously we cannot test that because we don't have all this time to wait for the result of the experiment. There are some experiments with the increased irradiation doses and so on, but it's not exactly it simulates part of the process, but not entire process. So this is the thing that we are, for now, we are able to say that definitely some of the microbes, but even some of the more complex organisms like lichens and fungi are able to survive a couple of years in space. We don't know yet if they are able to survive longer than that. Obviously, they are not doing great. So the survivability is decreasing quite a lot, but it's not impossible, especially if those organisms are not exposed directly to space, but are kind of embedded deeper within the rocks, which is not impossible. Third thing, they have to survive the landing. So this is one of the examples of rocks that were exposed at the edge of a rocket and then sent back to Earth to check how rocks that are being that have some organism inside will behave when they are going back to Earth. And apparently some of them were badly melted, which is not very, surprising. We know what happens to meteorites when they enter the atmosphere. You just heard about that. Part of that is just being melted. There's a fusion crust being formed. One looks like that. It's, couple of tens of degrees, even more. However, if we are just a little bit lower than that, we are really cool and fine, and we can survive if we are obviously, microbes. Not we can survive. If we are microbes, we can survive this trip, even without the space rocket. So, yeah, it's lithopenspermia still a very wild theory, but for now it looks as if it's not impossible. It may be shown that it's impossible in the future, but for now it's still a matter of study. So right now I'm going to talk quickly about my favorite topic, which is being killed by an asteroid. And I will start with someone that we should be very grateful to, which is obviously Bruce Willis. Yes, Bruce Willis, which saved us from the asteroid that was 1,000 kilometers in diameter, which would be indeed a very bad asteroid because it would create a crater that is about the same size as as Africa. Not great, depending on how it would hit. It could change the length of day by about 30 minutes. So it's nice that that Bruce Willis, thank you, saved us. But even with this size of the asteroid impact, it's very unlikely that we would have like a full impact sterilization. It's really like unless entire planetary surface is remelted, or large part of planetary surface is remelted, it's really hard to kill everything. Again, I'm not talking about us, I'm talking about microbes surviving. Sorry, we would be doomed. Why is it? Why the impact sterilization is so hard? Mostly because it's very heterogenic process. So for example, here you can see a rock or a cross-section through an impact crater. Pretty large impact crater with a lot of rocks that are here partially affected, but those rocks here, microbes in this location would be fine. We know that from those impact experiments with torturing the impact craters, they would be fine. Those rocks here would be maybe shocked to maybe 10, maybe locally 20 GPa. It should be fine. The parts would be indeed quite heated to quite high temperatures, and this is much more dangerous and hard for the microbes to handle. Of course, a couple of hundred degrees may be possible, but the temperature that is melting rocks, not so easy. So here you can see a piece of a suevite, which is a rock that was formed by an asteroid hitting the Earth in Germany about 14 million years ago. That is used to be a very nice piece of normal carbonaceous rock, so CaCO3. Yes, thank you, limestone. Yes, it was a nice piece of limestone, and then it was just messed up by the impactor. It was just changed into like a rock flour that was partially glued together by pieces of the of melt that you can see here as those darker blobs. Also, other rocks were intermixed, so it's a very complex rock. The point is that here you can see the rock that was heated above 1000 degrees roughly, and here you can see rocks just next to it that were much lower in temperature. And this is the worst part of this entire large impact crater, 24 kilometers in diameter. Only very small parts of those rocks here would be kind of hard to survive for microbes. All other parts here would be easy. So impact sterilization is very hard. Why then this impactor caused so much trouble? First of all, it did not sterilize the Earth. Yes, we are here. Even some, the chickens are here, so not all dinosaurs died. But still, it caused quite a lot of mess in our biological system. One of the largest dyings off was definitely caused by this impact. There were creatures that were definitely affected by the direct strike. So if you were somewhere here, you're a dinosaur, somewhere here, you were very lucky because you died instantly. You were up to couple of maybe up to 2000 kilometers from the point of impact. You would be just cooked very quickly. There is a gigantic fireball, very similar to what you can see if there is an atomic bomb exploding, maybe 1,500 kilometers from the point of impact. So very, very quick, easy death. If you are further away, you end up with the shockwave collapsing your lungs. Especially dangerous if you are a large animal. Smaller ones may be less affected. There is a gigantic winds, so you can just get be hit with a branch or something. There are options of dying, and of course you can be just hit with a piece of material that was ejected from the impactor at this location. However, it sounds bad, but it did not affect the entire globe. So what happened? Climate change. What killed dinosaurs? Climate change. But obviously not dinosaur-produced climate change, but asteroid-produced climate change. The thing that happened was the tsunami, yes, not great. The fireball, only very close to the impact site. In the past, there was a theory that maybe the re-entering of the ejecta that was launched during the impact and, for example, produced those impact spherules could have heated the Earth, the atmosphere sufficiently to produce global wildfires. Most probably not, except maybe in some extremely unlucky places that were anyway very susceptible to forest fires. But probably not the problem. The problem was the fact that, first of all, like someone mentioned, there was a lot of dust that was dumped into the atmosphere, which just blocked the sun and caused very rapid change in the climate. Second of all, there was a lot of both CO2 and sulfur pumped into the atmosphere, which means that it just put the entire global system into the very unstable situation, which means that the dinosaurs just could not cope with the quick pace of the climate changes. What about slightly smaller asteroids? So here is the site at the Reese crater. So one that is related to this nice rock here that you will be able to look at later on. The Reese crater was caused by about 1 kilometer in diameter asteroid. It's about 24 kilometers in diameter, 14 million years, so a long time ago. And you can see here this very small black thing here. And again, this is a piece of wood that was, if you have a trunk that was cut like that, this is a part of tree trunk that was just swooped into the entire mass of the crater, because the entire thing was covered in, again, couple of minutes with couple of hundreds of material that was not there before. So it's very locally very dangerous. Locally meaning, large part of Central Europe, because, for example, we can find pieces of this nice Bavarian location here. Find those pieces here in Wrocław, where I live, or very close to Wrocław. Those things are called tektites. Those are pieces of melted rock that was ejected from some of the impact craters and traveled very far away. Again, you could get hit by those things and burned very significantly, because this was very melted rock at the time of ejection. And even the crater, pretty small crater that you can see here, the 1.3 kilometers in diameter Berenger crater in Arizona, was again causing similar effects as I just discussed for Chicxulub, but in smaller scale. So again, the fireball up to about 10 kilometers, the collapse of lungs due to the passage of the shockwave up to 20-something kilometers, very hard winds. So the smaller the impactor, obviously, the less large area that is affected. So what about the craters that are the most often forming on Earth? This is actually my favorite topic of the studies, which are formed once every century, once every couple of thousands of years, very often, geologically speaking. So, for example, here you have the only Polish example of an impact crater called Morasko. It's located in central Poland. The largest impact, you can see here a couple of different round holes in the ground. Those are all impact craters that were formed at the same moment because the asteroid was crossing through the atmosphere and then disintegrated into smaller pieces that hit the Earth at practically the same time. The largest of those craters is 100 meters in diameter, but as I said, there are a couple of other ones about 40 meters in diameter and so on. What was done just a couple of years ago was a very detailed study of the material that is collected, that was collecting itself within a lake that is located only 5 kilometers from the point of impact. And we know the age of the crater here. And you can see that there is, this is just part of the data, but I didn't want it to just put all of the palynology and stuff like that. But there isn't much change. The point is that this impact crater, formation of this impact crater of this size, was not really seen far away from the impact point. Similar thing is related to Kali crater, which is very similar in size. Again, about located in Estonia. The largest crater is about 100 meters in diameter. There are other ones smaller around it. And for a very long time, it was thought that the analysis that was done in the bog that is located about 8 kilometers north from the point of impact was showing this dramatic change in the in how the environment looked like due to the impact. However, in the end, we figured that the date was not selected well for this analysis, and we don't think that this size of an impactor is causing large death zones around it. So, yay for us, because they happen very often. However, it doesn't mean that it doesn't cause death and destruction. It's just, it's very localized. So here you can see the again the Kali craters and the DEM digital elevation model of the largest crater, and we were digging here in the proximal ejecta blanket, so the material that was thrown out from the crater during its formation. This is just one of our outcrops, and what we found was pieces of dead bodies. We found dead bodies of organisms that were killed by an asteroid. Some of the dead bodies were just a couple of centimeters in diameter. Some of them were slightly larger. All of them were mostly spruce. So the trees that were growing nearby and had a very bad day 3,500 years ago because they were hit by an asteroid, and all of them died at the same moment. The interesting thing is that if you study this charcoal, study the dead bodies, you can figure out in which conditions the charcoal was formed. So what was the conditions within the proximal ejecta blanket at the time of formation? And apparently, first of all, this charcoal is very different from the charcoal that is formed during the forest fires. Second of all, it's quite low in temperature. So if you do some experiments, you can figure it out that the temperature of the proximal ejecta blanket was up to about 500, 600 degrees only. Interesting thing is that apparently all of the, or most of the impact craters all around the world have similar features. So this is what you should expect from those small impact craters. You do not have to evacuate, hundreds of kilometers, or tens of kilometers would be fine. However, whatever you will leave close by will be damaged, and we know that because after some very large digging in the literature, they kind of mention something like that in a couple of different papers. So how the trees died? Well, first of all, they were hit by an asteroid. They were damaged. We know that because one of the impact craters was studied very soon after its formation, Sikhota Alin in Russia, 47. And then parts of those trees have been mixed with the proximal ejecta blanket and just kind of slowly cooked inside. If you have listened to me, right now you can explain what's wrong with this movie. Any ideas? You know, if it's the comet or actually the comet was better choice than an asteroid because comet would be quicker or faster than an asteroid. But the second thing, absolutely true. I think that they said that it was about 6-7 kilometers in diameter, the asteroid. And even assuming that it would be a cometary body moving quite much quicker, let's say 50 kilometers per second, it would still not make a planetary destruction. So if anything like that happens to you, and you, for example, are multi-billionaire or something, do not invest in spaceship that will take you to the other planet that may be very dangerous. Just build a proper protection home digged into a geologically stable area. So you would be much better with that. So otherwise, I really enjoyed this movie, but this part really irritated me. So very quickly, in case you would like to avoid dying, there are ways for that. So first of all, we need to know what is potentially there in order to do something about that. You can see here the movie that is showing the number of potentially dangerous asteroids, but the point is that there is, until very recently, we didn't know about most of the asteroids that are potentially dangerous to us. But right now the number is growing. Right now, as for a couple of days ago, 2 days ago, 3 days ago, we known slightly less than 30,000 asteroids. But there are good and bad news on this slide. The good news is that most of the large asteroids, like 99% of large asteroids that can potentially, be the Chicxulub-sized asteroids, larger than 1 kilometer, so ones that can cause global or regional damage, we know about them. You can see that the number of those asteroids is not increasing. We are relatively safe from them. However, the smaller asteroids that can still be pretty dangerous. You remember the asteroid that did this large 1.3 kilometers in diameter crater in Arizona was 50 meters in diameter. Like most of them, we don't know about. And the number of them is growing very quickly, but still we have a lot to learn about. And so just, if you want to have some excitement in your life, you can check up the information about what's there flying around us today. Very good webpage. I strongly recommend checking it out. So today we have quite a lot of asteroids. As you can see, all of them were flying by us today. And even one of them was flying very close by, because it was flying closer than the distance between Earth and the Moon. So, yay, but missed us. So we should not worry about that. And you can see that there's nothing really large planned for us within the next couple of days. The largest one, I think is estimated from 30 to 70 meters in diameter. So again, potentially it could make the Barringer crater sized hole, but it will miss us. Don't worry about that. Or already, well, this one will miss us. Why do you think there is? There's a very exact number for the velocity, but there's a very large difference in size for the size of the impactor. Any ideas why is that? So the size of the impactor here, the largest one nearby, is from about 30 to 80, 90 meters, which means, yes, if the asteroid is dark, it means that it can be quite large before we'll see it on the dark sky. The asteroids are extremely small, and they can be seen only in a specific kind of. They don't. they are not like stars. They do not shine by themselves. So they are much harder to see, and depending on their albedo, they may be easier or harder to see. So those are actually the ones that we should worry about, but we should not worry too much. This is the list of asteroids that can actually potentially hit us. So here is the one that is predicted to potentially hit us in about 200 years, more or less. But the chance is extremely small. So do not worry about that. It's one in about 2,000 that it will not hit us. However, it's not impossible. And this is why we should keep an eye on those features and check out if they are there. There's a couple of things that we can actually do in order to avoid that. First one is obviously just kick it to a different location by, for example, exploding atomic bomb. Where have we heard about that? Yay, Hollywood. But it's an option. It's a very bad option. It's the worst option possible because it's a really, really unpredictable plan. So let's avoid doing that. Much better idea would be to send to the asteroid a brave group of painters to repaint our asteroid, because if we know about the danger in many years, many tens of hundreds of years in advance, even repainting the asteroid would change the way the orbit of the asteroid and help us to avoid the danger in a very predictable, very safe way. And the third option is to kind of kick it by either slowly moving it by a small rocket, or just kind of kick it, but with a smaller and more predictable, in a more predictable way. And if you don't know it, now you will. There's an amazing mission that is called DART that will be doing exactly that this fall. This fall there will be a first test of redirection of an asteroid. The mission is already on its way. It's going to a double asteroid, so an asteroid with a moon, small asteroid going around it, and it will impact the smaller asteroid to check if we can predictably change the way in which this system is moving. They are not right now trying to reach us, but we could use the same method in the past to save ourselves. On the less optimistic way of thinking about that, we can also use this method to actually put something to hit us. So, space terrorism will probably be an option after this fall. So, yay! Another end of the world. Here are some of the papers that I suggest to read if you are interested in the topic, and if you have any questions, I will be very happy to try to answer to them. And you can also talk to me later on. Thank you.